Okay, and so if you remember, this is the so-called KDD, data processing pipeline, and KDD stands for Knowledge Discovery in Database. So this is more from a database research community, but it also applies here, or what we will be following in this part of the module. And so last week, we focused on the pre-processing. So we talked about, for example, how to deal with missing data, and say, how do you calculate some basic and simple things, for example, how to aggregate data by binning, etc., etc. And then today we're going to focusing on this part. So we will not have like a separate lecture, just talk about transformation, and which is most about, for example, changing the format of data. We'll kind of talk about that as last week as well, for example, mapping and categorical values into numbers or other way around. And here, this week, we're going to start talking about the data mining part of the pipeline. And we're going to spend a couple of lectures because there's lots of different things you can do here. Okay, and let me now switch to this week's slide. Okay. And so this week, we're going to talk about the descriptive data summarization, which is essentially the different statistics you have on data and distance measures. And so we all know you can measure distance. Usually in the real world, we will say, okay, from say school to, okay, from university to your home is 2.3 miles. And that's based on the Euclidean distance. And there's many other different ways, and some other distance metrics might works better for the computation or the analysis we want to do. Okay, and we'll start with the descriptive data summarization. Okay, and to better understand data and in terms of tendencies, variation, and the spread. And so this again is mostly from the statistical point of view. And this is useful, for example, you have a very large data set, and let's say, I don't know, the transaction records of the supermarket, and you get, I don't know, hundreds of thousands or even millions every day. And if you want to look at the data over a longer period, like a year or even longer, you have lots of data. And one thing you want to do before you actually do an analysis is to understand what data looks like. And this is where the data summarization might be useful. Okay, and so the simple thing you can do in terms of summarization is data dispersion characteristics. And so that's a kind of a fancy name, but you know most of these already, the median, mean, and maximum, mean, quantiles, outliers, and variance. And so most of these have fairly clear definitions. What they are. Outliers is slightly different, but we'll go through all of those. Okay, and in terms of data dispersion, it means analyze with multiple granularity or precision. Okay, so you could, for example, analyze the data at the most detailed precision. For example, just look at the raw data, each individual numbers, or you could look at the most, how do I say, not growth, had the highest level, the most, or the least precision, where you look at the entire data set, calculate some, say, max, min, quantiles, etc. Then you don't look at any individual at all. But then you can also have other granularities in between the most detailed and the least detailed ones. Then depends on the your analysis. For example, you might aggregate data, depends on the product or regions, And then that's something in between the most detailed ones and the least detailed ones. Okay, and we're going to introduce box plot later on if you don't know that yet. And it's most related to the quantile, which is the concept, and related to the mean and median. Okay, and finally, we're going to talk about a little bit more about more advanced computations and in terms of folding measures into numerical dimensions. And so I believe this is about the dimensionality reduction when, for example, if you happen to have a very complex data and it's maybe you have hundreds of columns, usually that means hundreds of different dimensions, that will be too many. You might want to find a way to reduce the dimension for the analysis. Okay, so we're going to go through each of these in more details and during this lecture. Okay. So we start with the more basic concepts, and many of you probably know these already. And the first one is the mean, and so that just if you don't understand this formula completely, that means you add up all the numbers in the collection and then divide it by the number of numbers you have. So but that's the average. I'm sure most of you would know. The median means the middle value. And if you have an even number of values, so that you don't have the one in the middle. For example, if you have 4 numbers, 1, 2, 3, and 4, there's no middle value. So instead, you take the middle 2, so it will be the 2 and 3, and calculate the average. In that case, will be the median. And then find mode. Mode is a value that occurs most frequently. Okay, gonna look at the example now. Let's say this is our data collection. And if we want to calculate the average or the mean, you add all these numbers together, so 13, 18 together, and then divide it by how many numbers you have. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's total 9 numbers, and you do that. Do the division, and you get that's the mean or the average for your data set. Okay, and so the median is the middle value. So in this case, you need to first sort numbers, otherwise you don't know which one is in the middle. And if you're given this one, you say, oh, 13 is in the middle. That's not the case. You need to sort numbers and then pick the one in the middle. In this case, will be 14. And so you can see middle is different from mean. That's usually the case. And sometimes, and they are exactly the same, but that's rare. Okay, and so this is just how do you find the middle one. As we said, and if you have an even number of numbers, okay, yeah. Okay, and then the last one is mode. And if you remember here, mode is the number that occurs most frequently. And so you just look at these values, say 13 occurred 4 times, 14 twice, 16, 18, 21 only once. So this is the one that occurred the most frequently or the most number of times. So the mode will be 13. Okay, and this is the second example. And then here we have less number of numbers in the collection. But in this case, we have 6, which is an even number of numbers. So to calculate the mean, it's the same. You add these all number up together and divide it by 6. Okay, and the only difference here is calculate median, because there's no one single number in the middle. So instead you take the middle 2, which is 5 and 7, and then get the average of those. So 5 plus 7 divided by 2 give you the 6. And okay, and can I ask, say for this example, and what is the mode for this collection of numbers? Anyone? And you can just type in the chat. No, no one knows what is the mode. Okay, and someone said 6, 5, yeah. Anyone else? Oh, and so the mode is the number that occurs the most frequently. So in this case, I think mode will be 5 because it occurred twice, and all the other numbers only occurred once. So the mode in this case will be 5. And so the mode is actually has nothing to do with the median or min. For example, if we look at this previous number, the mode is 13, which is actually the minimum number you have. So it could be the maximum number as well. So really has any relationship with what the median or mean is for the data collector. Okay, so we're still going through the kind of relatively easier measurements or statistics. And I think this one probably most of you would know in terms of the minimum, that's the smallest number. So if this is our data collection, 3, 7, and 3, 7, 8, 10, the smallest number is 7. This is quite easy, especially if you sorted the collection of the numbers. And then for this one, because it's not sorted yet, and certainly shouldn't be the 24, and it's the smallest one, not the first one in the sequence or the collection. So it's much easier if you actually first sort the data, and you can see the minimum is 15. Okay, and so the maximum would be the opposite of the minimum, which will be the largest number in the collection. So here, and it's quite easy, it's already sorted, so you can see the largest number is 10, so the maximum is 10. And then for the second example, again, it's not sorted, and so it's much easier if we sorted the first, and then we can see the maximum is 28. Okay. So the next one, the concept maybe less of you would have heard of, is called a quantile, and you probably would have heard of the term like a quarters. That means 1/4. So it's a similar concept here. Okay, and then so the quantiles are the numbers. In this case, we have 3 numbers which divide the data into 4 equal sized groups. So basically, we have a collection of numbers. We want to divide them into 4 equal sized groups. So if you think of last week, we can talk about, say, you create different bins. So this is like we want to create 4 bins, and what we called equal depth bins we mentioned before. So each bins contains the same number of numbers. And in this case, the entire collection is already sorted. And so the first quantile would contain or has 25% of data below it, or to the left it, or smaller than the first quantile. And then between the first quantile, or let's say, okay, and so the second quantile of Q2 has 50% of data below it. So this is essentially the median. So if you remember, median is the kind of number in the middle of the sequence when it's sorted. And so then to its left would have half of the entire sequence or collection. So that's here the same. And this is also means, and between Q1 and Q2, you have 25%. So because let's say below Q1, you have 25, and then between Q1 and Q2, you have 25. So below Q2, in total is 50. And then similarly, and below Q3, you have 75%. So that means between Q2 and Q3, you have another 25%. And so this left another 25% that will be above Q3. Okay, and if we need to find the quantiles, first, and it's very important, is to order data, because the median or the quantiles, and it doesn't really work if there's a sequence of data is not ordered. And for to find Q2, you just find the median. As I said, it's the same thing. Okay, and then for the Q1, you can just look at the lower half of the median. So you have the median, then you have the left half and the right half. And for the Q1, you just look at the median of the left half. So that's what will be Q1. Essentially, you divided the left half into 2 equal sized bins. And then for the Q3, you look at the right-hand side of the half. Again, find the middle or the median of the right-hand side. And that will be Q3. Right-hand side give you the up 50%, and the median will be divided that into 2 equal sized parts. Okay, so we can do this. Say this is the sequence we already ordered. That's very important. If it's not, and you have to make sure it's ordered. And we can start with the median, which is the middle. So that's the Q2, the second quantile. Okay, and so then they divide it into 2 other ones. And this is actually the smaller part. Usually that's where the Q1 comes from. So this will be the top part, and this will be the middle of the top part, and this is the bottom half, and this will be the bottom. So this will be the lower quantile. Oh, that's interesting. Okay, and also this is the minimum and this is the maximum, which we already covered it before. Okay, and so this is the next concept, and which is called range. And range will be the difference between the maximum and minimum number. So you need to find the minimum and maximum value. Once you sorted the sequence, that's quite easy to do. And the difference between them is the range. So in this case, will be 32 minus 1, which gives you 31. Okay. And so the interquantile range, so that might be new to some of you, and is distance between the lower quantile and the up quantile. And so we already said, and the up quantile is 7, the lower quantile is 20. So the interquantile range is 13. So you can see an interquantile range is not always just half of the entire range. Yeah, that's not always the case. Okay, and so we used all these different concepts, and use this is for the something called the box plot. And so this is the box plot, and it has a box here, which actually this says the interquantile range. That's where the names come from. So that's interquantile range, or the IQR, interquantile range, that's it. So it has a box and then 2 ticks at the end. So this is the minimum value, this is the maximum value. So this indicates the range of your data, how they are there. So the data will be definitely within these 2. And this one, the box in the middle, is starting from the first quantile and end with 3rd quantile. So it will be under. Actually, this one will be upside down. We'll start 1 from bottom 37 here. But the interquantile range is still this part. So this is where the box will be. And within the box, you still have another line. This line will be the medium. So that's where the middle of the entire sequence is. Okay. And so this is providing some kind of summary of or description of the entire data set. And you can see the medium itself is a bit different from the mean, which you actually can't really see from here either. But you can actually roughly get the idea. So this is the entire range, but the number distribution is not entirely even. If it's even, then the median will be somewhere in the middle. You can see the median is more on the bottom. So that means that the data is kind of skewed towards the lower value part. That means there's more, how do I say? There's more value or more numbers of the values. It's smaller values, basically on this end. Okay. And once you have all these different measures, especially the interquantile range, which is the distance between the first and third quantile, and you can define outliers. So that means the data doesn't quite fit into the entire data set or the general trend. Okay. And one possible definition of outliers is data points so that more than 1.5 times entire quantile range from the median. Oh, sorry, it's below the first quarter or above the third quarter. Okay, so this is my interquantile. And this is my box, and this is my interquantile range. And if I take this distance, and times 1.5, 1.5, and then go either this way or this way. And if that point is still beyond that extended range, that we consider as an interquantile, sorry, as an outlier. Okay, and this is you can decide whether it's 1.5 times or 1 times or twice interquantile range. That's something you can adjust. But the concept, if you look at this part, and if you extend it from first quantile further down for another 1.5 interquantile range, that would cover the entire data set. So there's unlikely to be any outlier on this side. Whereas you extend this part this way, you take this distance and times 1.5, there is chances there might be some values here, might be outside and becomes an outlier. Okay, for example, this is a simple example. So we have 1, 2, 3, 4, 5, 6, 7 numbers. So this is the median, it's already sorted, because it's in the middle. And that's the first and third quantile. So that's basically the median of the left half, and this is the median of the right half. Okay, and if we can calculate the interquantile range, which is Q3 minus Q1, give you 3. Okay, and if we do this times 1.5, just 3 times 1.5 would be 4.5. So you either extend to the right, and so 7 plus 1.5 times 3 give you 11.5. So that means everything bigger than 11.5 were considered as an outlier. Similarly, on this end, and you further extend 1.5 in the quantile range, but for this side, left side, and it's become smaller, not bigger. So you take 4, then minus 1.5 times the interquantile range, which is 3, that give you minus 0.5. So that means if any number is less than, so that's further outside minus 0.5, that becomes a outlier. So in this case, nothing is outside this range. There's no outlier. Okay. Okay, and so this is again some from kind of, how do I say, unfairly common statistics, and I hope most of you would have heard of it. And it's called standard deviation. And what it does intuitively is to calculate how far away, on average, how far away each point are from the median, which is the middle. Sorry, not median, the average or the mean. So that's what this formula says. And so this is the mean value. So that's the average, which you add all the numbers together and divide it by a number of numbers. And then here it says, take all the numbers, calculate their distance to the middle or the average. Okay, and so these values can be positive or negative, because if the number is smaller than the mean values, then it will be negative. But here we're only interested in distance. So we don't not care whether it's minus or positive. For example, and if it's something is less than the average, and it's a very small number, like a -10, that means still very far away from the middle. And just to remove the sign, whether it's positive or negative, so we do the square. Also do the square, that's why we also have this square root, just to take away and the impact of the square here. So we add this square, distance square together and divide it by total number of records. So that gives you an idea of how far away are all these points from the mean value. So this is not median, it's the mean value. Okay, and this is an example. So that's your sequence. And to find the mean, you add them together and divide it by number, total number of numbers. So in this case, 5, give you 76. And then you calculate the distance of each of these numbers from the mean or the average. So this is called a deviation. So some of these are positive and some of these are negative because they're actually smaller than the mean. Okay, and in this case, because we're only interested in distance, we're not interested in size. And so we do the square of these first. We square all these numbers, so the whole number becomes positive. Add them up, give it this, divided by the total number of numbers, 5. And finally, calculate the square root and give you some numbers. So basically, the bigger this number, that means the further away the points you have, or data points you have away, they're further away from the average or mean. The smaller the numbers, the closer they are to the average. Okay, and let me see if I can find an example. Okay. This is maybe not the best example, but you can see in this particular case, if we look at the variance along the y-axis, and it's 0, because actually all the points have exactly the y value, and which is also equal to the mean or average. So then the distance between each point to the average or the mean will be 0, and you add them up, still 0, divided by total number here is 8, still 0, and square root is still 0. So in this case, you have 0 variance. That means all the data are exactly the same as the mean. That's the extreme cases. And then you have other cases, for example, this ones. That's actually like the more common ones, and which we'll also see later on. It shows the distribution. Then this will be your mean. And then the variance shows how widespread the data is. Maybe I'll show you a different picture. Okay, maybe this will be the better one. And so if you look at this one, okay, so I have these two distributions. So this is the x-axis is the value, and the y-axis shows how many points have that value. So one is taller and narrower, the other one is lower and wider. That means there's more points in the middle, and this one is less points in the middle. Okay, between these two, and does the left one has higher variance or the right one has higher variance? Can you type in the chat? If you think this one has higher variance, just type left. And if you think this one has higher variance, just type right. Anyone? Okay. Have a couple of people says right. Anyone think it's left? Okay, yeah, so that's correct. So the right is the answer. In this case, you can imagine the mean is probably here, and you have more numbers along this in the mean because it has, sorry, because it's higher, this indicates number. So that means there's lots of numbers which has 0 variance close compared to the average. Where here, there's a less number in the middle. That means there's more numbers. They don't have 0 variance. They're further spread out. And this one would have a larger variance. So this is what a larger variance looks like when you draw it. And this is a smaller variance. And for 0 variances, you have all the points along in the middle, as we saw before. That's the 0 variance one. Okay, and back to the slide. Ooh. Okay, and so yeah, this is similar to the curve we saw before, and the x-axis shows the values of your data range. So this will be the minimum, that will be the maximum, and for example, let's say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, something like that. And the y-axis counted how many numbers you have for each value. So you have maybe only one number, 0, have 20 for 1, 50 for 2, and this is 4, you have more, and it goes down. Okay, and here it says called a symmetric data. So symmetric data means this curve is symmetric in the sense, so this will be the mean or the middle of the curve, and this half, the left half, is identical to this half. So the left half is the same, exactly the same as the right half. So that gives you a symmetric curve. And then in this case, the mean equal to median, if you remember. So the mean is the average of all the numbers. The median is the middle number. And because this is symmetry, and the median is the same as the mean, and the same as is mode. If you remember, mode is the number that appeared most frequently. So basically where the peak is. In this case, the peak is at the mean or the medium. So that's where also the mode is. Okay. Here it talks about, but usually the data distribution data you have in the real world is does not like it looks perfectly symmetry like this. And so the peak could be to the left of the mean. And this is we call, or to the right of the mean. Okay. And in both cases, we call them skewed data. So that means that the curve or the line is not symmetry, and basically the middle of your data set is closer to the lower end or closer to the high end. So when it's closer to the lower end, it's called positively skewed data. In this case, the mode is here. The mode is always the number that appears most of times. That's always the peak of the line. That will be the mode. And then the mean will be here, and the median will be somewhere in between. Oops. Okay, so this is the opposite, whereas there's more numbers towards the higher half of the data. And so the mean will be here, mode will be here, again, where the highest the curve is, and the median will be somewhere in between. Okay, and so this is a kind of yield distribution. And so there's the global, so this is like the wealth pyramid. And at the bottom, and you have lots of people which has their income is less than $10,000. I assume that's 1 year. And then further up, you have a much smaller portion of people. So population-wise, this is 71%. A smaller percentage, still quite significant, 21%. And the annual income is, or total wealth is between $10,000 and $100,000. That's quite a bit. That's the total value. And further up, and these are the people with $100,000 to $1 million values, and that's account for 74%. And then for the people with more than 1 million wealth, it's a very small number. It's 0.7%. Okay, and let's say, and you have the x-axis. If you look at these one, the x-axis is the wealth, how much money you have. So on this end, you have very little money. On the other hand, you have lots of money. So this starts from 10,000, less than 10,000, all the way to here, more than 1 million. And the y-axis will be the population. How much people is within that particular range. So for this one, particular one, and is it a positively skewed like this or negatively skewed like this? So the x-axis is the wealth. The y-axis is the percent or the population within that house range. So you can see for the lower income has the highest 171. This, let's say the middle, which has 21% and 74%, so 7.4%, and finally 0.7. Okay, so you can decide whether this is a positively skewed one or negatively skewed curve, or maybe you think it's a symmetric curve. Can you type?
It's positively skewed.
Sorry?
It's positively skewed.
Okay, and someone says positively skewed. Anyone else?
It's kind of obvious, like the low income has the highest population.
Yeah. Anyone would think it's maybe negatively skewed? No, yeah. And so the answer is positively skewed, because if you look at this number, you would know on this part of the curve, the income is quite low, less than 10,000. It has very large number, 70 something percent, 71%. So the value here is high. Whereas on this side, and you have lots of wealth, but the number is very small. So on this side, you have over 1 million, but the value is only 0.7%. So this side will be much smaller. So you have this kind of positively skewed curve in terms of distribution of the wealth. So the majority of the population have not that much wealth, whereas a small part, very small part of the population has a large amount of individual wealth. So if you look at these numbers, you can also see, so this 70% of people owns only 3% of the total wealth, whereas here you have 0.7% of the population, which owns almost half, 45.2%. And I think the kind of this, how do I say, this kind of inequality, no, this kind of skewness is actually further increased over time. That's usually the richer people get richer and the poorer people get poorer. That's the general trend, which is not the right thing, but unfortunately, that's the case most of the time. Okay, and so this is about different measures and concepts, mostly on the box plot. Okay, and next part, we're going to talk about data types and distant functions. Ooh, why is this moving by itself? Hello. I think the slides is just moving by itself for some reason. Transition. Yeah, okay, and so it's not jumping again. Okay, so we talked about these different data types before. Previously we called attribute type before, and when we talk in the first part, talk about different visualizations, we said there's categorical data. Well, here they call nominal data, and which you can say, for example, the color, or whether it's beer or bread or peanut, and the product type. These are nominal, and you can just say they are different things. You can't say which one is bigger or smaller. There's no order. And then it's not ordinal data, and ordinal data, you have some order, but you can't really do computation. So the one we did, examples we had before is dress size, and you have small, medium, and large size. You can say, okay, smaller is less than medium, which is again less than the large size, but you can't do, say, small plus medium. It doesn't really make sense. And you can also have grade. You can have A, B, C, D. You can't say A plus B equal to something. It doesn't make sense. And there's the numerical ones. And these are the numbers, basically. And you can have intervals and ratios. And we'll talk a bit more about those later. Okay, the categorical or the nominal data, these are categories. And this is also usually what we call qualitative data. And previously in the last lecture, we talked about you can potentially map each category to numbers. And that's possible, but also you have to be very careful. And once, for example, you map male to 0 and female to 1, it kind of gives them an order, especially if there's more than 1. That means male is smaller than female, which is not an order, in the original data, because for male and female, it doesn't really have any particular order. So the examples of nominal data, including colors and genders, anything that's a category. Or you have, say, I don't know, IT products and furnitures. Okay, and for the nominal data, and all you can do is just to say whether they are of the same type or different type, equal or unequal, so equal and the same. And we already said, and these are called the qualitative attributes. You can't do any quantitative and computation on it. Okay, and so in the context of classification, if you remember, so classification, if you don't know, is almost like you have many different categories, which is called classes in this particular case. And almost also like you have different bins. You need to put all these items into different bins. Each bin is one class. And in this here, with a nominal value, you can do classification. You can put items into different bins based on their values, nominal values. But because these are nominal values, you don't have an ordering, so you don't know which bin is before or after which bin. Okay, and then the next one is the ordinal, which you actually have an order, but you don't have a distance. And so the dress size, and you would have an order, but you don't have small, medium, large, but you don't have a distance. Okay, and then you have the rating of how effective a person is. You can say the person is effective or not effective, but there's no distance of so-called distance, and effectiveness distance does not exist. Hang on, yeah. Okay, and again, so you can, for this type of ordinal data, and you can say whether they are same or not the same. So the equal or inequality, equality or inequality. But also you have orders, so you can order them. So you can decide whether it's less than or more than. Okay. So here, for example, you have the first, second, and third. There may be a competition or the race. And you can say, you would know the first, for example, is faster than the second, which is faster than the third, but you don't really know how much difference that is. So maybe the first is only 1 second faster than the second, and then which the second is then 2 minutes faster than the third. Okay, and so finally, and we have the numerical type of attributes. Again, it can be ordered, and it should also have a distance. So this becomes numerical or quantitative, as we said before. So it can do all sorts of operations. So whether they are equal or not, it's the same as before. And you can also order them. You can do less than, more than. So that's the same as ordinal. And then you can also do various calculations. You can do addition, subtraction, multiplication, division, basically all different calculations. Okay, and so then we're going to talk a little bit about distance functions. So as we said, this last type, which is numeric, which actually you can calculate distance. So the distance only applies to the numeric type or the quantitative type, not to the ordinal or the nominal categorical values. For those two, you don't have distance. Only apply to the numerical ones. You can calculate distance. Okay, and you may think this is probably straightforward.
Sorry to disturb you. I have a question based on the standard deviation.
A question about what?
Standard deviation.
Standard deviation.
Yeah.
Okay. So standard deviation is something unrelated to the variance.
No, it is related to the variance actually. Variance is dependent on the standard deviation. How
No,
far
I
each and
didn't say
every
they are
point
the
is
same.
deviated
I
from
say
the
that they
mean.
are related.
Sorry?
I did not say the two are the same. I say that they are related.
Yeah, they are related, correct?
Yeah.
Yeah. Joe, I just
So-
wanted to ask you, like while using the formula, when do we apply like n-1 and n? Is it depending on the population mean or the sample mean?
Sorry, the what?
The standard deviation formula. You do remember like the square root of x minus x bar upon n.
Okay, so
Yeah.
can we discuss this after the class? Okay, we didn't cover standard deviation here.
But we are
Yeah.
covering variance, so standard deviation should be covered.
So the standard deviation, I think for the class, all you need to know is something similar to the variance. It's used to measure how far away the points are
Points
distributed
are
from the
deviated from the
middle.
mean, correct.
Okay, it's a slightly different measure. We're not going to discuss here now. If we have time, we can do it after the class.
Sure, after
Yeah.
the class, we'll discuss here.
Okay, and back to here. Okay, so we're gonna later talk about and when you calculate distance. So obviously, so first, most of you think you know distance. You have two numbers, and the distance is one minus the other one. Yeah, that's correct. And also, this is for an 2D distance. So you have a triangle with straight points. Then you can calculate the distance between these different points. Okay, and you can say the distance between I and J was this line is greater than 0. So we don't know exactly that is, but we can know it's definitely greater than 0. There's a line in between this. Okay, and distance I and I. So the distance between a point and itself is always 0. And then the distance between I and J is equal to J and I. Okay, that's not always the case, but in this distance, the distance from I to J is the same distance from J to I. And then finally, this distance between I and J, and this one, that is the distance. It's less than these two add together. So it's less than I and H and J add up together. Okay. And so all these holds true and in what we call the Euclidean distance. If you use some other distance metrics, which we'll see, hopefully see later on, it does not always true. And so the Euclidean distance is what we use kind of by default. And for example, when you talk to someone, actually, yeah, okay, what are the, so if you're doing your geometry lessons or exercise, or you to calculate distance between points on a plane or even 3D, and that's the one we use all the time by default. But actually there are, and so I'm not gonna explain. I assume you know how to calculate Euclidean distance, and you have the difference between the x and y, and if you have 3 dimension, you have z, and this distance is squared, and then add them together and get the square root. But in the real world, and there's or in theory, there's many different possible and distance metrics. And for example, if you want to calculate, say using Google Map, I want to calculate the distance between home and university. So it's also calculating the distance, but what it gives you is not a Euclidean distance. In the sense, you are not calculating a straight line from your home and to university, because that's not actually the actual path you can take in the real world. Essentially, in the real world, and the path actually may have to go here, will be, say, different line segment, depends on the actual road you can take to. That will be the distance between the home and university. So that essentially is a different distance matrix. Okay, so these are some of the examples and might look a little bit abstract. Okay, and so someone asked, is Euclidean distance the minimum distance between 2 points? And the Euclidean distance, so between 2 points, for any particularly distance metrics, you have only one measure, or only one value. So if I give you 2 points, X and Y, and if I want to know the Euclidean distance between X and Y, there's only one value. There's no bigger or smaller value. And then
I think that's what I'm saying, that there may be different distances between 2 points depending on which path you are taking, but this Euclidean distance is the one which is like straight line, and it is the minimum distance possible between 2 points. Maybe we can discuss in the class or
Yeah,
lab.
she is correct. Actually, that is the minimum distance. It is basically using Pythagorean theorem.
Yeah,
Using
I
the
know.
Cartesian coordinates.
So, but say it is minimum because you're only considering the Euclidean and say path distance matrix. But if you use some other distance matrix, and for example, you can define the matrix, which a distance matrix, which only consider X coordinates. That's still a valid distance matrix. The distance matrix doesn't say how exactly you calculate it. It's just a formula.
Okay.
Obviously, in the real world, that's maybe physically it's not plausible, but it's still a distance matrix in theory, and it
Like
might
how
give you
physically
different
not
values.
possible in real world?
And also we don't know. For example, you can do time travel. You can swap space and time, and you can travel between A and B. Then distance becomes 0. These are the things much more theoretical. But
Okay, like how
let's say
time
Euclidean
travel distance becomes 0? Can like please elaborate?
Sorry?
Can you elaborate what you just said, the time travel thing?
No. So these different matrices, they have different ways of calculating distance.
Yeah, they are using the modulus to get rid of the negative sign, as the distance cannot be negative in few cases. I can say Manhattan distance.
Sorry, some of the negative what?
Yeah, they are adding modulus to get rid of the negative sign in the Manhattan one and this thing, LP metric, Minkowski distance.
Yeah, so all these different, okay, so these different distance metrics, and the only thing you can say about them is they try to meet these requirements.
Correct, that is the Pythagorean theorem, like I said.
Sorry?
It is the Pythagorean theorem, basic, the theorem, what Euclidean distance means. The reason they are using x2 and x1 because it can be on any plane. So we have to cancel out to get the vertical distance between x2 and x1.
Yeah, so any formula which meet these 4 requirements, you can call it a distance matrix. That's not too difficult. So there's many different possible definitions. And these are the ones people actually use the more. There's lots more obscure distance metrics people doesn't really measure, doesn't really use. Okay, so for example, and so these ones are probably, so you have the Euclidean distance, which you're familiar with. Then this number here, it doesn't have to be 2, it can be 1, which will then become this, or similar to this, or can become 3, 4, 5, which becomes this one. And this is a different distance measures, and it measures pairwise distance, and it just picks the maximum between any dimensions. And so you have these ones. So you compare the difference between x1 and y1, and then distance between x2, y2, and all the way to xd and yd. And you just pick the maximum value as the distance. Okay, so this one the last one still meet these requirements, but it doesn't really say apply to, it's still a distance matrix, doesn't really useful, for example, calculate travel distance in the real world, but in some calculations and will still be useful. But essentially that just means when the p-value here becomes very infinitely big. So that sign means infinity. And so that means if the p is infinitely big, so think of this as big a number as you can think of. So the largest distance will have a much bigger impact compared to any other smaller distance, even if it's just tiny bit smaller. That's why it's essentially it just becomes using the distance between the largest pairs. Okay, and also all these are more or less just extension of this distance matrix. So you have 2, you have p equal to 1 or p equal to infinity, and there's also other distance matrix not based on this. Okay, yeah, and so the Euclidean distance is most common. We already know because that's kind of default, and it's also when we talk about distance, if we didn't say which matrix it's based on, and it's probably Euclidean. Okay, and the Manhattan distance is this one, and so just intuitively you can think of. So the Manhattan distance is like you need to get from A to B, and you have to travel on a kind of grid of streets. That's the Manhattan distance. Let me see if I can find the picture. Yeah. So maybe just like this. So you need to travel from A to B. So this is the Euclidean distance. And the Manhattan distance is you can only travel along X or Y directions. You can't go any, say, diagonal directions. That's give you Manhattan distance. And so if you take either the blue line or the green line, they are both Manhattan distances. And even the shape is different, the distance, the value is exactly the same. Because if you add all these and X segment together, which give you this one, and add the Y segment together, always give you this one. So the value is always the same. So for example, and this one, so this line will be a Manhattan distance, whereas this blue line is not. It's traveling not always along X or Y this axis. And then if you have 3 dimensions or 4 dimensions, so long as it's always travel along the axis, and that will be fine. So that's something like this. So again, you have the green line, which is Euclidean. The red and blue and yellow are all Manhattan distances. The different paths, the shape looks different, but they are exactly the value is the same.
So like when to use Euclidean distance or the Manhattan distance, it depends on the dimensions.
No, it doesn't depend. It depends on your application. What you're talking about. Say, obviously, if you talk about say traveling in the real world, or say you're calculating distance for geometry, you use Euclidean distance. Maybe say when you calculate distance in travel distance in the real world, maybe Manhattan distance will be a better case, because that might be closer compared to Euclidean. It's better approximate over the actual path. There's some other purely abstract calculation cases, then the other numbers might be make more sense. It really depends on the analysis problem.
Can you like give me an example like for the Manhattan or the Euclidean? Where can I use it? Real life example I need.
Let me see if we do have any examples. Yeah, and maybe we'll have some examples of other distance matrix later on. Okay, yeah. And this is the first examples for using Euclidean distance. And we're looking at the temperature of different cities at different months of the year. So for London, so in July, the average is 20, August is 18, September is 10. I'm not sure if it's a real number, looks quite low. And then similar for Edinburgh and Leeds. Okay, and you can calculate the temperature difference between London and Edinburgh. Okay, so you pairwise, you calculate the different. So essentially, in this case, we have a three-dimensional point for each city. So for for London, you have 3 dimensions, which is mapped to July, August, and September. So 20, 18, 10. And for the Edinburgh, there's also these 3 dimensions. You have 16, 12, or 6. And you calculated the Euclidean distance. And so you can definitely calculate any distance metrics. Yeah. And whether that gives you a lot of sense, maybe not. Okay, and you can calculate similarly, and the temperature distance between London and Leeds give you this much. So if it's smaller, you can know this is smaller. And then the Edinburgh and the Leeds, this is this much. So, and okay, and in the real world, okay, so if you have, this is your data, and if you want to say, how do I say, and in the real world, if you want to calculate the temperature distance between 2 cities, and usually what would you do? Will you use Euclidean distance or use some other way to calculate the difference? Anyone?
Like what you asked, can you please repeat?
Okay, so if you were to calculate the temperature difference between London and Edinburgh, will you use Euclidean distance or use some other way to calculate?
Euclidean will be better.
And anyone else?
Because it also
Okay,
uses in the
let's say,
KNN clustering.
can you think
so
of any
that
other
will be better.
ways when you calculate the temperature difference between 2 cities? Forget about distance, just say, I have 2 cities where I have, say, the average temperature for each month. You need to calculate the difference between the temperatures. Is there any other way?
Just to calculate the difference, just subtract them.
Sorry?
Just subtract them. Take the slope if you want. Gradient.
Okay. And anyone else? I'm not sure I understand. Okay, so one other way you can do is you can calculate the difference for each month and then do an average. So you can say the distance between July is 4 degrees, between August is 6, and between September is 4. And then you can do an average that give you some other numbers. Yeah. That's another way. It's not necessarily, this is not necessarily a distance matrix, but that it can tell you, okay, so on average, what is the difference between the temperature between the 2 cities? And you could use an Euclidean distance that also give you some measures, which is a bit different. Maybe not as easy to explain or interpret it compared to, say, the average of distance by month. Okay, and anyway, so come back to the continue on, and so use all these distance we calculated, and we can build a distance matrix. So you have all the cities on the columns and the rows, and then in the cell is the difference between the cities on the column and rows. So here is the difference between London and itself, so it's always 0. So that's between Edinburgh and itself is also 0. So the same city by itself is always 0. So diagonal is always 0. And then the difference between Edinburgh and London is 8.25. That's what we calculated here. And then between London and Leeds is 2.45. Again, what we calculated. And finally, and between Leeds and Edinburgh is 6.16. And then the other thing you can see is this half and the top half, the top right half and the bottom left half is the same. And because the difference between London and Edinburgh is the same as Edinburgh and London. So we said the distance between 2 points, if you just switch the start and end point, the value will not change. Okay, and so really only this part is useful and this part is kind of duplicate. So you always know the diagonal is always 0, and then this part is always same as the bottom part. So you can just keep 1. You don't need the other one, which you can. And so this is the so-called distance matrix. And you can imagine you can have more items, more than just 3 cities. You can have many more. And then the distance itself can be calculated using different metrics. Okay, and so then the distance for different, this is distance for different data types, and it can be either interval scaled or ratio scaled. Okay, we have about 10 minutes. Okay. So interval, just basically think of a range. You have an x-axis, you can have an interval start from 1 to 2, something like that. And so it's continuous, it can be any values, and the intervals can be positive or negative in terms of the distance. And so most of these numerical values are interval scaled, and it can be, say, the height itself, it can be positive or negative. The height itself is a continuous value, so it can be any value. If you talk about the height of a person or height of a thing, usually it can't be negative, but it has to be positive or 0, but it's continuous, it can be anything between 0 and very, very large number. Okay, and you can measure it using the matrix we discussed. And then you can also have ratio. Ratio is basically just the, how do I say, the proportion between 2 values. So you can have the ratio between 2 height or 2 weight, or even the height and weight, sorry, height and width, or even height and weight. Okay, so the ratio itself is a bit different. It just says how many times the difference. And you can also use log transformation. And so you can say is, instead of just say it's 2 times, it says 2 to the power of how many times is the difference. Okay, and so this is another way, or this is, again, it's not quite in terms of difference. Sorry, this is not a distance measure. It's a different way to measure differences. So if you have kind of 2, let's say 2 points, it has many 2 high dimensional points, they have many different attributes, and you can measure how many variables or attributes for these 2 data points that do not match or match. Then you can say to how similar or dissimilar these 2 points are. Okay, and so if we say here we have examples for hobbies, you have 2 person, there are 5 different possible hobbies. If a person like a hobby and it will say don't like this hobby, or say 0. If they likes it, it will be 1. And you can compare how many of these values are same or different to say how this similar or dissimilar these two persons are. So here it says similarity and coefficient. Then it's looking at the measurement which they are the same, or the variables or the attributes they are the same. In this case, they both like swimming and hiking. And the distance, similarity matching distance, is just 1 minus the similarity matching coefficient. So if there are two the same, then a different one is just 1 minus that. Uninformative. Okay. And so this one, this similarity matching coefficient can lead to a different distance matrix and called Jaccard distance. And it is based on whether they are similar or not. Different dimensions, whether they are similar or not. Okay. And in this case, B and C are similar, and then divided by all the possible ones, so that also including the A, which is dissimilar. And what it ignores, that's the thing, so it ignores, and is whether they are both negative. So if you look at this one here, we have singing, and both Jim and John, they don't like singing, but that's not included. That's just by definition. So similar here for this one, which is negative for both, or 0 for both, it's ignored. Okay, let's see how we are doing in time. Couldn't see what is the time now. Okay. Oh. We have these variables. Gower distance. Okay. I'm not gonna cover. So these are some more advanced topics, and in terms related to distance matrix, aggregated, binary, interval scaled. Yeah. So I mean, these are not actually needed for the coursework, and if you're interested, you can have a look. And those is actually more of theoretical values, and compared to the actual, it doesn't really use it that much. Yeah, okay. And so if you're interested, you can email me and we can discuss some of these. And otherwise, I will just stop the lecture here now.